Okay, so welcome back to our evening or afternoon session. So today we have Radouane, who will continue with the second lecture on Ostrogotsky Instability. Please, Radouane.
Okay. Well, thank you. Good evening, or maybe good morning for some people. The takeaway message of Monday was that if we have higher derivative in some Lagrangian, tomorrow I will go into really building new theories of gravity, etc. But so far we are a bit general about the ideas. So the message was, if we have higher derivatives and if the Lagrangian is non-degenerate, then we have a Hamiltonian which has a linear momentum. And I was commenting that this is a problem. So let's see, why is it a problem today? So we will, instead of working that generically, better to go with some specific models and just to study that. So I will go with that with a beta over 2 phi squared. Phi is some field, and of course I have that the derivative with respect to the highest order term is equal to 1, so it's different from 0. So it's non-degenerate Lagrangian. Okay, see, if we calculate the variation of that, we get the equation of motion, which is 4th order. I'm not going to do the analysis, Hamiltonian analysis, etc., but we have 2 degrees of freedom. And we have this equation of motion, which is a 4th order. All right. This is a complete free theory. It is a linear theory, the linear equation. There is no some nonlinear terms, so there is no some coupling, etc. What we can look for are solution of the following form: exponential I omega t. Well, replacing in this equation will give me an omega 4 plus alpha omega squared plus beta equal to 0. Well, we search for the solution of this equation, and we find that there are 4 solutions, which are going to be minus alpha plus or minus the discriminant, which is alpha squared minus 4 beta, divided by 2. All right. So the point is, what we want to fix is that we don't have any runaway solution. What does it mean? That we don't want some solution which goes to infinity. So we don't want runaway solution. So that means that omega has to be real. If omega is real, we have just oscillations, and then we don't run into problems. If omega has some complex part, because we will have always both conjugate values with a plus complex and minus complex, one of them will diverge exponentially. So we want to impose that omega, the 4 roots here are real. And imposing that condition is that alpha squared minus 4 beta has to be positive, first of all. We need to impose that alpha is negative and that beta is positive. Well, these are the conditions that we need to impose in order to don't have any instability, in the sense that we have a solution which runs to infinity. Now, let's rename a bit this solution. The omega plus, or omega plus squared, I will call it omega 1. And what it is, it's equal to minus alpha plus the square root divided by 2. And the omega minus squared, I will call it omega 2. And this is the minus alpha minus square root over 2. Well, from that, I can deduce alpha and beta, and I get that alpha is minus omega 1 squared plus omega 2 squared, and beta is omega 1 squared, omega 2 squared. Fine. So what is the Lagrangian that I have? The Lagrangian is 1/2 phi double dot squared. Remember that it was plus alpha over 2. So it's minus omega 1 squared plus omega 2 squared over 2 phi dot squared plus beta over 2. So plus 1/2 omega 1 squared, omega 2 squared, phi squared. Okay. And this is a famous actually model, which is called the Pais oscillator. Pais oscillator. So in fact, we started with some theory of the following form, with alpha and beta can take any value. And we are asking that exist some solutions which are not diverging. So in that sense that we have some classical stability, and that stability imposes some condition. So these values will be translated into alpha, which should be negative, beta, which should be positive, and alpha squared minus 4 beta, which is positive. So that translates into that, and selects only one theory, which is going to be this Lagrangian, and it's called the Pais oscillator. Well, and here we see that we have a solution which is stable. What is the solution? Is phi of t. This Lagrangian, we can solve it. There is no, I mean, the equation of motion, even if it is fourth order, it is a linear solution. So the solution is pretty simple. And we have, of course, 4 constant of integration. This is a cos omega 2t plus d sine omega 2t. Fine. So it's a well-behaved solution. So it's quite strange now. Finally, we were all Monday talking about that when we have higher order derivatives, actually it should produce some problems, etc. And finally, what do we have is a solution which is oscillatory, it does not diverge. So why did we take a full course class on that actually? Well, the reason is because it's a free theory. And in fact, let's calculate the energy to understand a bit. So we can calculate the Hamiltonian and get the energy. So if we replace that solution, we will get the energy and get that it's 1/2 omega 1 squared minus omega 2 squared. And we get a squared plus b squared omega 1 squared minus c squared plus d squared omega 2 squared. Okay. So let's suppose that omega 1 is larger than omega 2. For example, that this is positive, this is positive, this is positive. What we have is that we have positive energy and negative energy. And here it's not a problem. Why? Because it's the free theory. So it's just that they are decoupled. There are some negative energies, there are positive energies, there is no problem. The problem will appear even if there are negative energies and positive energies that are completely decoupled. But if we put some interaction, that will couple the positive and negative energy, and that should trigger some instability. And this is in fact what we will see. So if we have a free theory, usually there is no problem. And the same thing will happen in the quantum theory, in the sense that we will see that the 2 Hilbert spaces can be just factorized. So let's add some interaction term. So free theory, even if we see that there are some positive and negative energies, well, it's harmless. So we add actually some interaction terms. So what I will do is add a lambda over 4 phi 4 in the Lagrangian that I had before. Well, now we have to do again the analysis. So what I will do is that I will build the Hamiltonian. From the Hamiltonian, we'll get 4 equations. And what I will look for, I'm looking just for the classical stability so far. So we'll look to equilibrium point. The equilibrium point is the stationary point where the time derivatives are 0. And this is going to be called a vacuum. And I'm asking that vacuum should be stable. Okay. And we will see that there is some stability, in fact, but in general, it's unstable. And then we go to the quantum aspect of this problem. Okay, so we have this Lagrangian. I'm going to use the same trick by that told us Dirac. So I will change the phi dot by a psi. So I will get a Lagrangian, which is psi dot squared plus alpha over 2 psi squared plus beta over 2 phi squared minus gamma, because I already used lambda, phi minus, psi minus phi dot. Okay, so I'm just adding like a constraint. So when psi is equal to phi dot, I replace it and I'm getting the same thing. And I forgot the last term, the interaction term. Otherwise, we know what will be the result. Okay, so this is the Lagrangian I want to study. And the only difference, remember, I added this interaction term. So it's the coupled Pais oscillator. Well, we have two variables. I have phi and I have psi. To each one I will associate some momenta. This one I will call it pi with Poisson brackets, which should be equal to 1. The p is going to be the variation of the Lagrangian with respect to phi dot. The pi is the variation of the Lagrangian with respect to psi dot. Well, we can do this calculation. This is gamma and this is psi dot. Fine. So I can calculate the Hamiltonian. It's going to be pi psi dot plus p phi dot minus the Lagrangian. Okay. We do these calculations and we get that the Hamiltonian is pi squared over 2 minus alpha over 2 psi squared minus beta over 2 phi squared plus lambda over 4 phi 4 and plus that linear term, which is a characteristic of these higher derivative terms. Fine. Now I can calculate the equations of motion. Phi dot is going to be the Poisson bracket of phi with the Hamiltonian, and this is going to be psi. Psi dot is equal to be psi with the Hamiltonian. So that is going to be the variation of the Hamiltonian with respect to pi, which is going to be pi. The p dot is going to be the variation minus variation with respect to, how did I call it? I call it phi. So this is equal to beta phi minus lambda phi cube. And the last one is pi dot, which is pi h and is equal to alpha psi minus p. Okay, so these are the equations with the coupling term lambda. Fine. So what do we ask for? We are looking, usually, if you have some harmonic oscillator, etc., there is some point which is the minimum of your potential, which is going to be the vacuum. Here, in fact, there is no really a minimum. So we extend a bit the idea of a vacuum. So I will call the vacuum the stationary point. So this is in a dynamical system, what is called the critical point. So it's looking for the point where all derivatives are equal to 0. Okay, so looking to this point, which is the stationary point, we will call it the vacuum and see what is happening around it. Here, the solution is simple. Psi has to be 0. If psi is 0, p has to be 0, pi has to be 0, and this has to be 0. So we have psi equal to pi equal to p equal to 0. And at the same time, we have that phi is equal to 0 or phi is equal to beta over lambda square root of this plus or minus. So we have, in fact, 3 critical points. Well, then what we can do is check the stability around these points. So we have some points in the phase space, which are the stationary points, and we want to see, so the stationary point means that the flow of evolution does not evolve anymore there. If we are there, we stay there. And now we are looking around it. So we make a linearization around each of these critical points, and we see if we are going to converge towards the point, it's a stable point, or we go to infinity. That will be an unstable point. So what you do is just that you do a linearization of our equation. Let's call that psi 0, the critical point. So we have some phase space, we have a critical point here, and we are looking something around it. So the equations of motion around this critical point will be, let's call them delta phi, delta psi, delta p, and delta pi, by defining delta phi is equal to phi minus phi 0. Phi 0 will be 0 or this, for example, etc. So it's just making a linearization. So here we have only psi, so that is already linear, multiplying delta phi, delta psi, delta p, and delta pi. Fine. The psi dot is pi, it's already linear, so it 0, 0, 0, 1. Then we have p dot, which is this. So I have to make a linearization, which is going to give me beta minus 3 lambda phi 0 squared, 0, 0, 0. And the last one will be 0 alpha minus 1, 0. Okay. So this is the linearization around the critical point. And what we are asking is that if, well, we know how to solve this kind of systems. They are linear. We are looking to the eigenvalues of this matrix. And once we have the eigenvalues, we have the solution. So what are the eigenvalues? Usually we write the eigenvalues lambda, but lambda is the coupling now. So how I will call it? I will call it E as eigenvalue. So E squared is going, we have 4 eigenvalues. It will be alpha plus or minus alpha squared minus 4 beta plus 12 lambda phi 0 squared divided by 2. Okay. So the system is linearly stable. I'm talking just about linear stability if the real part of this is positive. So we have some eigenvalues. The solution, sorry, I'm saying stable, unstable, of course. The solution will be exponential of epsilon t. Epsilon can be imaginary, so you will have the real part times t plus I times the imaginary part times t. So what matters is this part. So if the real part is positive, we get, we are going far from the point, so the point is an unstable point. Fine. So we can look to our points. We know the coordinates. One is phi 0 equal to 0, so we remove it. Beta and alpha, we know them also. They depend on omega 1, omega 2. So if you do that, what you will find is that the point with phi equal to 0 is linearly stable. And the other points, the plus or minus beta over lambda, are linearly unstable. Okay. That is just the linear stability. We don't know about the nonlinear stability. Fine. But at least there is one critical point which might be nonlinearly stable. What I mean by that, remember what we were doing in order to be sure that this is the free theory. What we saw is that the free theory has solutions which are totally bounded, that are not diverging. Now we added some coupling, and what we want is to see around some point, around some critical point, some vacuum, if we still have this bounded type of solutions. What we saw is that there are 3 critical points. Around 2 critical points, we have an instability. around 1, we have at least linear stability. It means that if I move a little bit, I stay around it, but it's just the linear stability. If I want to study the nonlinear stability, I need to do it numerically and solve these equations, which we will do. And for that, I will share a Mathematica file. So here it is. And here I wrote the equations. This is the equation. There is this, well, fourth order differential equation. What we have is that I fixed omega 1, omega 2 equal to 1. In fact, you can normalize everything. Most exactly, I took omega 1 equal to omega 2 for this calculation, for this special case. And you can solve the differential equation. So I took around the critical point, all these derivatives, I took them equal to 0. And the phi 0, remember that we are looking to the critical point where phi 0 is equal to 0. So I move a little bit next to it, some value c, and I would like to know how much I stay or not around it. So it will depend on c, this initial condition, and it depends on the coupling. How much coupling do I put? Okay, so let's solve that. This is the solution, for example, fixing lambda equal to 1. And the coupling constant, I will, the initial condition, sorry, I will put it to 0.1. So I'm very close to the point I had. So that is the solution. You get oscillation. It's a bit strange oscillation because you have exchange of energy between the positive and negative modes. Well, we can also make the plot of psi as a function of psi prime, psi as a function of psi double prime. It makes some nice plots. You can study that in that phase space, see all these quasi-periodic trajectories that you have, etc., etc. Well, it's not the objective of my of this analysis. What I want to see is instability. Here, the solution is stable. It's just oscillating around our point. Let me increase a bit more, and this we knew it. If we take very small initial conditions, this is the linear stability. It's okay. Let me go a bit more far. Still, we have stability. If I take 0.3, that diverges. Now I have a system which diverges totally. In fact, what is the critical point is 0.29. And this it can be proved. There is a critical value. So there is some kind, which is sometimes called an island of stability. If I am around that vacuum, then the solution is stable. It's oscillating and it stays there. I'm here in the full nonlinear regime because I'm solving totally the equation. If I take initial conditions far from this island of stability, that I diverge and go to infinity, so we get that instability. So let me go back. Well, and that you can, of course, in fact, if you let it run enough, it will fill all the phase space here, etc. Okay. So let me go back here, share content screen. So what we have learned from that is the following. We have a phase space. There is a point, some critical point. And around this critical point, this is what we can call an island of stability. And what is happening is that if I take initial conditions, which was this parameter C, if I take an initial condition here, my system stays here. So here I have stability. I don't have runaway solution. If I take an initial condition which is large, it goes to infinity. So this is like some domain where we have stability. So what we learn from that is that we still have negative energies and positive energies, but somehow the negative energies are not destabilizing enough the positive energies and does not produce this runaway solution. So the Ostrogradsky instability is not always bad classically. Most exactly, what it tells us is the following, is that an instability could exist. We have something which is a linear term that can produce instability, but that instability is there, but it has to be excited somehow in order to produce something which is physically observable. So in some situations, so it will depend a lot on the coupling that we put in the nonlinear regime, not the free theory. In the free theory, everything was stable. So we put some coupling, which is lambda phi 4. And we found that in that case, there is a regime where, in fact, we don't excite that much and we keep it stable. But if you change the coupling, you get another coupling. For example, you are looking to a theory with lambda phi 3, maybe it will be always unstable, etc. So it will depend a lot on this type of coupling that you have and on the initial conditions. So the instability exists, but it will not be triggered necessarily. It will depend a lot on the initial conditions. So we have a vacuum. If we have fluctuations around this vacuum which are small, maybe the solution might be stable. So we can still use this type of theories depending on the coupling that we have. But if the fluctuations are too large compared to the vacuum solution, that we run into problems. Okay. So that is more or less some simple analysis of the classical part. And what I would like to see more, a bit more now, is the quantum part, because we call it the Ostrogradsky instability, but we call it also the Ostrogradsky ghost. So why do we call it a ghost? Well, let's now pass to the quantum theory. So we have this Lagrangian. I will keep the free theory. We can add, of course, the coupling term, but that will just make things more complicated. So let's keep the free theory like this. And we have omega 1 squared, omega 2 squared divided by 2 times phi squared. Okay. Now this Lagrangian, this is the Lagrangian that we had at the beginning, and the free theory. And I would like to quantize that theory. I will use canonical quantization. But for that, first of all, I will rewrite it differently, because with higher derivatives, things are not that trivial. So let me write another Lagrangian, which are totally equivalent with two fields, minus phi dot psi dot, minus 1/2 psi squared plus omega 1 squared plus omega 2 squared times phi dot squared minus omega 1 squared, omega 2 squared, phi squared. Okay. So I'm saying that these two theories, they give the same equations of motion. The reason is, if I do the variation with respect to psi dot, it will give me phi double dot equal to psi. So if I replace then back into the Lagrangian, I will get a minus phi dot, phi triple dot minus 1/2. This term here will be phi double dot squared. Here I can do an integration by parts. It will give this. So all this will give 1/2 phi double dot squared, which is the original one. Fine. So I will look to things in this way with this new Lagrangian, because now I have only first derivatives. And at the same time, I will do a change of variables. So I will consider that x1 is equal to omega 2 squared phi plus psi, and x2 is omega 1 squared phi plus psi. This maybe, the free theory here, it's the linear theory. So so here there was a question in the chat. The first equation that you have, this is a total linear equation. So if you have different modes, in fact, they separate. They don't interact between them. So if you make, for example, you work in the Fourier space, you get each mode, which is a different equation, and you solve them separately. So in that sense, it is free. If you have a nonlinear term, like phi cube, then even if you go to the Fourier, in the Fourier space, you see that you will get modes which are coupled to each other. So you don't have this, this separation, in fact. So when you have nonlinear terms, this is when the theory is not free. Okay. So we have this this Lagrangian, and we do this change of coordinates. Okay, x1, x2. Why? Because in fact it will simplify a lot, because we will recognize directly some Lagrangian that we know, and that we know how to quantize it. So in fact, I just have to replace here. So we replace, we do the calculations, simplification, and what you get is the following. So I will assume that in fact omega 1 is different than omega 2. If they are equal, it's a bit longer, the calculation, but it can be done also, because I will divide. In fact, you have to divide, so you have to assume that they are different. And we get this minus x2 squared minus omega 2 squared x2 squared. Here I forgot a squared. Okay. So now we can, of course, always this minus sign will appear in some places, etc., which tells us that some problem will appear. Okay, we have a simple theory with 4 variables, x1, x1 dot, x2, x2 dot. I know exactly how to deal with this theory. So we take the momentum associated to the variable x1. So x1 dot, that is x1 dot divided by omega 1 squared minus omega 2 squared. The same for p2, etc., etc. You build the Hamiltonian. Well, they are just, in fact, 2 oscillators. So you will get omega 1 squared minus omega 2 squared divided by 2, p1 squared, plus omega 1 squared divided by 2, omega 1 squared minus omega 2 squared times x1 squared. And the same thing with a minus sign, 1 over omega 1 squared minus omega 2 squared over 2, p2 squared, let's put some parentheses, plus omega 2 squared over 2 omega 1 squared minus omega 2 squared x2 squared. So in fact, we have 2 harmonic oscillators, one with a sign plus the other one with a sign minus, which we understand will possibly trigger something. Okay, we have the Poisson relation like this, commutation, the brackets, Poisson bracket. So this, for the canonical quantization, we replace that by operators and with the relation that this is equal to E h bar, and with x2 p2, putting this x2 equal to I h bar. Okay. So from that, we can calculate, this is just the harmonic oscillator. We know what is the energy. So we will have some quantum state, which is going to be characterized in this case by 2 numbers, because we have 2 harmonic oscillators. And the energy, which will depend on these 2, will be, as we know, h bar omega 1 over 2, n1 plus 1/2, minus h bar omega 2 over 2, n2 plus 1/2. So we, at the quantum level, we have, well, two harmonic oscillators. Again, they are decoupled. but with N1 and N2, which are positive, strictly positive. Not strictly, sorry, which are positive, which are integers. And what we see is that there is no ground state. Well, and this is usually what we will consider as a problem. We have different ways actually to see it. Some people prefer to look at it in this way, but why some people say that there is a ghost? This is more like historically, let's see how to do it. The reason is the following. What we can just do like that there is no ground state. So there is some instability there. But let's do it in a different way. Historically, it was done like that. We consider the ladder operators, which are the A and A DAG operators. So let's define that the X, either X1 or X2, remember, so let me call them Xi. It's gonna be H bar over 2m omega I. So just to remember a bit classes of quantum mechanics. And Pi is going to be, and at the same time, we will need that formula later on. So let me write them. And I get the A DAG minus AI. Okay, fine. So I can get A and A DAG, etc. So I can replace my Hamiltonian. I can write it in that way. I'm getting A1 DAG, A1 plus 1/2, and minus H bar omega 2, A2 DAG, A2 plus 1/2. Okay, with the condition that AI DAG is equal to 1, which comes directly because the X and P, the commutator is I H bar, which comes directly from the Poisson bracket. Fine. Okay, so we have this relation. So what we can do is the following. Let us look to A2 DAG minus or equal to A2 DAG A2 plus 1. So this A2 DAG A2, I can replace it by some A2 DAG minus 1 with a half, it gives minus 1/2. Fine. So let's do it in this way. Historically, at least it was done like that. It's just a way to see what we call a ghost. We can think of some state which has this property, let's call it phi or 0 or whatever we want, that A1 with this is 0, and that A2 DAG with that state is 0. So that will be our vacuum. Let's define it in this way. Why not? It's a problem, but we will see. If I calculate the H over that state, what I will have is, because the A1 over phi is 0, I'm getting just the H bar omega 1 over 2. And here, because the A2 DAG over phi is 0, I'm getting the minus with this minus, which means plus, H bar omega 2 over 2. Okay, this phi. And this will be like the energy of my, the lowest energy, in fact. Why? Because we can define, now from this vacuum, I can define a state N, which is going to be the standard A1 DAG n times over the square root of n factorial of this vacuum. And M, which is going to be with A2, but not DAG, because for A2, the DAG, like it's the opposite of what we know usually. So n factorial over phi. So let's suppose we want to calculate the state 0, 1. So what I'm saying is that the phi is the vacuum. So for the two oscillators is 0, 0. Now I want to calculate the state 0, 1. Okay, fine. Why not? I take my Hamiltonian, which is here. The calculations are simple. H bar omega 1, A, let's keep it like that. A1 DAG, A1, 0, 1, plus 1/2, 0, 1, and minus H bar omega 2, A2 DAG, A2, 0, 1, plus 1/2, 0, 1. Okay, so what we have is the first one, the A1, which acts on the 0, it's 0. Well, this, it stays like that. And here, what we are going to do is that we know that the 0, 1 state is equal, and this is defined here, is equal to the A2 times the state 0, 0. So this that. So we have the A2 DAG. Here I did I miss some factor? No, it's fine. Just that I think yeah. Here, where is it? My Hamiltonian. Hamiltonian is here. In this expression, I will, as we said, we will just commute these two into A2 DAG minus 1. I don't know where it was, this formula. I know I wrote it somewhere. So here in this one, I will write it as A2 DAG and minus 1. So with the other one, it gives half. So A2 DAG, and this will give me the A2 0, 0. Okay. So doing the commutation again here, the A2 DAG A2, it will give me an A2 DAG minus 1 acting on 0, 0, but the A2 DAG that gives 0 on the definition of our vacuum. So you get just minus times A2, and minus A2 is minus 0, 1. Fine. So doing all these calculations at the end of the day, or just at the end of 1 minute, what you get is the vacuum, omega 1 plus omega 2. That was what we thought to have, plus H bar omega 2, everything multiplied by 0, 1. Maybe there is a factor half. Okay. So in fact, actually, the spectrum is positive definite. And you can continue like that. We defined a very, very weird vacuum. Usually you define it in this way. But I decided, because the one with the index 2 had some kind of strange index here, strange sign, sorry. It has a minus sign. I decided to inverse what is creation and annihilation and just define it in this way. Why not? We'll see what is the problem. But if we do that, for the moment, what I can find is that this is a vacuum. It has a perfect energy, which is the following. And then all the states which comes after that, they will all add actually some energy, and the spectrum is completely positive definite. So what we did is just that we renamed A2 into some B2 DAG and A2 DAG into some B2. So what is creation? I call it annihilation. What is annihilation is called creation. Historically, it was done like that, and this is why it is called a ghost. The problem with the following are two problems. First problem, so we have a positive spectrum, but first problem is that, remember, I said that I defined the vacuum in this way. So now we have to go back to what is A2 DAG. It's X, well, there is some coefficient, minus H bar over M omega 2, the derivative applied over psi equal to 0. Usually, when we are doing A2, we get the same equation, but with a plus. And when we solve that equation, we get an exponential minus x squared. If you solve this equation, you get an exponential plus x squared. So you have a wave function which is not normalizable. That's the first actually problem. The second problem is that, and this is why it is called a ghost, let's take the state 1, which was, we said that we will call it like that the operator A actually is the creation operator. And let's calculate the norm of that state that we built in this way, 1, 1. Well, it's 0, A2 DAG, A2, 0. Using the commutation, this is A2 DAG minus 1. So A2 DAG over 0 should be 0, and it gives me minus 0, 0. First, this is not normalizable, but let's suppose that we manage to normalize it in some way. What I get is a norm which is negative. And this is why we call it a ghost. So there is two ways to look at it. Either you say that energies are going negative, there is no ground state, or you can change what you call creation annihilation. But in that case, what you are winning are negative norms, in fact, in your spectrum. But the energies will be positive, but with negative norm. Okay. So, and that is negative probability. So you lose completely our understanding of quantum mechanics. So of course, we don't like that, of course. Well, if there are no interactions, we don't have any problem, because in that case, we have what we have. So this is just two ways to think of it. Let's go back to for me, the simplest one is just to look at with normalizable wave functions and with norms which are all positive. I think it's much better to think of it in this way. But it was just to see why we call it a ghost. So we have energies which are going to minus infinity, actually from minus infinity to plus infinity. These actually are completely decoupled at the free theory, at the linear theory. So we have two harmonic oscillators which are completely decoupled. Now, if we add some coupling, now we can start interacting with between both, and the matter can be interacting with that. So matter, normal matter, for example, if this describes some exotic field, matter will be coupled to that, and this is free energy, because that state can always go to lower and lower and lower energy and excite matter all the time. Because the universe is not in an excited state all the time, we believe that this is impossible. So we should have a ground state, which is quite fundamental in order to explain our universe. So this kind of situation should not occur. But again, it will depend a lot on the coupling to matter. So if I have to conclude on that, we have an instability which is called the Ostrogotsky instability. It comes all the time when we have a non-degenerate Lagrangian with higher derivatives. Now, at the classical level, we see that it depends a lot on the coupling to matter or to any other field. If this is a free theory, we don't care about the instability. If there is coupling, then we can excite possibly this ghost and produce some problems. But it will depend on the coupling and on how much we fluctuate around the vacuum. In the quantum theory, it should be the same, even if things are not totally clear, but it should be the same. That also it will depend on the coupling that we should have to matter, and how much we excite this ghost. Some people believe that in this case, if in the classical theory we have an island of stability, we should have a quantum theory which is not that bad. We can live with it. And there is a paper which is called Living with Ghosts of Hawking. We can live with that finally. It's not that much problematic. But if the classical theory, you have only runaway solutions, you have collapse, it means that your solution, in fact, and I will finish with that. I didn't talk about collapse now that I remember, and we finish with that. When we have this, I was saying that when the fluctuations are large, imagine that we start at 4. In fact, what is happening is that here I integrate up to 10,000, but in fact, after some point, the system diverges completely. So it's not that we have an instability which is exponential, that we diverge exponentially, that we have something which is called collapse, that after a finite time, we get a divergence. So in fact, in that case, you cannot integrate the system for longer periods. And this is really problematic in physics, that we cannot continue our system because it has a singularity. So it's a singularity which comes at a finite time. We don't know if all Ostrogradsky instabilities come in this way, but it is possible. Well, in fact, with that, I finished. Just summarizing again the takeaway message of today, and tomorrow I will go to specific models. It will be a bit more clear why we did this analysis. Hi, yeah, that's.
Thank you, Radouane. So